Welcome to this video on the core concepts that will bring us all the way from large language models to scientific AI agents. Some scientists have frankly been hiding under a rock, seemingly trying to ignore the AI revolution and the impact it has on science. And I can sort of understand them. It's an area full of exaggerated claims, and you constantly hear "this changes everything," as well as "this will end humanity," almost every week. I find neither to be useful, and I'm not trying to tell you which side you should take. Instead, I hope to provide a foundation that will give you an informed opinion. I'll start by talking about large language models, which leads into retrieval-augmented generation, tool calling, the model context protocol, agent skills, agent harnesses, AI agents, and finally, AI scientists. Let's start with basic LLM usage. This is probably what all of you are already doing. It has three parts: you the user, a client, and a large language model that is the brain of the operation. The user writes a query, hopefully including the relevant context. The client sends it to the large language model, which provides an answer. The problem with this setup is that it relies way too much on the large language model knowing everything. There are gaps in the knowledge of any model, and when you run into them, you see what is referred to as hallucination. That is, the model makes up things that are not true. The question is thus, could we somehow help the LLM? That leads me to retrieval-augmented generation, or RAG as it's called. In this setup, the user writes a query, and we now immediately do information retrieval. That is, we try to find relevant information to the question. This could be in the form of text snippets from the scientific literature or structured data coming out of a biomedical knowledge graph. The client then sends the query plus this context that we've identified through information retrieval to the large language model, which answers based on the context instead of just based on what it knows itself. However, retrieval is hard. It requires you to understand a complex query, find all the required information, and in this case, not drown the large language model with noise in the form of irrelevant information. However, large language models are pretty good at this, so could we not let the LLM itself decide what information it thinks it needs to answer the query? That idea leads us to what is called tool calling. Tool calling is a way for a client to provide functions that the LLM can choose to call to request information. The setup now looks like this. The user talks to a client that provides both a user interface for the user and tools for the LLM. The user queries the client, and the client adds functions as context, sends it to the LLM, which can then call back with function calls. When it does that, the client executes the function calls and replies with the information it has looked up for the LLM. Eventually, the LLM will answer the question when it thinks it's gotten all the required information. The problem here is that there may be numerous functions that you need to implement, and the client has to implement all of them, leading to an unmaintainable monolith of a piece of software. The solution to that would be, can't we make it distributed? And yes, we can. That is the whole idea of the model context protocol, referred to as MCP. This is a way that allows online tools, such as bioinformatics resources, to provide LLM functions by hosting MCP servers. The setup now looks like this. The user talks to the client, and the client talks to both the LLM and the MCP server. You can have multiple MCP servers in play at the same time, and the client acts as a proxy that's routing information for both the LLM and the MCP servers. The LLM still does function calls. It knows nothing about MCP. The client takes the requests, sends them to the right MCP servers that execute them. Still, this approach often fails, especially when the LLM has to combine multiple different functions to solve a task, and it has to pick the right functions out of a too big library of functions. Can we somehow solve that by prompting the LLM in a smarter way? That is what led to what is called agent skills. This may sound fancy, but agent skills are really just text files with recipes that explain to the LLM how to solve certain specific tasks. It is a form of shared prompt engineering, if you will. A bioinformatics example of a skill would be step-by-step instructions on how to do RNA-seq analysis. For the skills to work, they need to be added as context. And the question is, who's going to add those skills based on the question? The answer to that is agent harnesses. OpenAI Codex, Claude Code, and OpenClaw are probably the three most famous agent harnesses. Fundamentally, a harness is an orchestration system that manages everything and keeps prompting the LLM until the task that you gave it has been completed. However, a harness is not an agent. So what is an agent? AI agents are what you get when you bring it all together. The user will often have several different ways of communicating with the harness, which retrieves skills, talks to the LLM, as well as MCP servers. To have a successful agent, you need a good agent harness, a large language model that is the brain of the operation, a good skill collection for what you want the agent to be doing, the required skills to support it, and an execution environment in which to run them. Agents can be incredibly powerful and work on tasks for hours at end. But, as we've also seen in software development, you can very quickly spend much money on tokens for the LLM, and it can be a security nightmare. For that reason, harnesses also need to worry a lot about access permissions and guardrails to make sure that nothing bad happens. AI scientists. There have been many misleading headlines claiming that AI scientists are already now solving scientific problems and even running entire labs. In my opinion, reality is a lot more boring. AI scientists can solve tasks within narrowly scoped domains when you provided them with the tools to do so, and even then they lack scientific creativity. Within bioinformatics, many agent systems have been developed, starting with Biomni, PromptBio, Pantheon OS, and ClawBio. There are many more than these. All of them are agent wrappers for tools that allow you to automate bioinformatics analysis with varying success. The stochastic behavior is, in my opinion, still a big problem, and for that reason, I do not trust them so far. Let me summarize. Modern AI agents have many parts. The LLM is the brain of the operation, however, it is only one of many parts. AI has already changed coding, and it will for sure change bioinformatics in the near future. However, I do not believe that it will replace bioinformaticians. The reason for that is that if you cannot do a task yourself, you cannot check if the AI did it right. That is true for bioinformatics, and is true for any other task you want to automate with AI. That's all I have to say about AI agent systems this time. If you want to learn more about large language models, I suggest you watch this video next. Thanks for your attention.